In the final clip, we're still solving polynomial inequalities, but these polynomial inequalities, they say, have unusual solution sets. So we're going to look at a couple variations of what can happen when you're solving polynomial inequalities. The first one that we're going to look at is 3a. It says x squared plus 2x plus 5. Again, it's a quadratic equation. It's already set equal to 0, but I immediately noticed that I'm going to have trouble factoring this x squared plus 2x plus 5. So as soon as I recognize that, I'm going to go to some graphical evidence to try to help me figure out what's going on with this curve. So I already have it loaded in the equation editor on the calculator. I'm going to do a graph of this and then use this graph to help me figure out what's going on with this. So if I look at the graph, I know that this graph will never have any x-intercepts, which means if we try to solve this, we're going to solve using a quadratic formula. We'll get complex solutions, which means we're going to have i's in them. We'd have to take the square root of the negative. But there are no real x-intercepts. So if there are no real x-intercepts, the graph never crosses, so it's never equal to 0. So when we interpret this inequality, they say this is an unusual solution set is, where is our curve greater than 0? Well, greater than 0 means where are the outputs of this graph going to be higher than 0, and that is always. So can't mark on there with my marker like I thought it could, but there it goes. But it will always be greater than 0. So really in 3a, our solution set is quite simple. It is from negative infinity to positive infinity. So they say that's a little bit unusual because you don't have any x-intercepts, so you'd have to consider all the solutions. In 3b, we have exactly the same equation on the left-hand side. Our inequality symbol has just changed, and it said where is it less than or equal to 0. So in 3b, go back to our graphical evidence. I mean, it didn't change the nature of our graph at all, but our interpretation of it is a little bit different. This time it's saying, where are all of your outputs less than or equal to 0? Well, our graph is never less than or equal to 0, so this means we have no solution. So there are several ways to represent this. One way that we looked at earlier this year in Chapter 0 is the empty set. Another way is to represent a null set. So one or the other, it doesn't matter which one you choose. Both represent the same concept. Okay, so now we'll look at 3c and 3d. They're both related to each other except for the inequality signs. So for this one, the first thing I want to do is I want to make sure I get set equal to 0, so minus 2x. And then I want to add 16, so it's going to be plus 1 is less than or equal to 0. This one will factor, but here's what's a little bit unique about it. It's going to be x minus 1 times another x minus 1 is less than or equal to 0. That is the correct factorization of it, which means we really only have one related 0, and that is when x is equal to a 1. So our graph would have to be, here's our x-axis, our number line, here's 1. Our graph is going to have to smile because of the positive leading coefficient. Quadratic squared is a U-shape, so it's going to come down here. It's going to touch and be tangent and come back up because it has multiplicity of 2. Again, if I wanted to, I could rewrite this statement as x minus 1 squared is less than or equal to 0. So it's a good reinforcement of our ideas of multiplicity. If a factor has a multiple, is represented multiple times, and if it's squared, it's going to be tangent, which means it touches but doesn't cross. So it's asking you, when will our graph be less than or equal to 0? Well, what is unusual about this solution set is that there's exactly one solution. When is it less than? Never. But when is it equal to 0? Only when x is equal to 1. So the solution set can be represented simply by saying the solution set of 1. When we go to part D just flips the inequality sign around a little bit. So instead of having the x squared minus 2x plus 1 and being less than or equal to 0, it's saying where is it greater than 0. And the only thing that's unique about this is it's everywhere except at 1. So at 1 it's equal to 0. We just want it to be greater than 0. So our solution set's going to go from a negative infinity up to 1 but not including it, union it with everything bigger than 1 but not including it to infinity. So just be aware that you can have unusual solution sets. Make sure that you look at your graphical evidence and put it together along with your interval notation.